right, section 24.8, multi-step synthesis with diazonium compounds. The key to understanding when you need to use a diazonium compound is illustrated in this dibromotoluene molecule starting here on the right. Now, what kind of director is a methyl group? In electrophilic aromatic substitution, it's an ortho and para director. What kind of director is a bromo? It's an ortho and para director. So none of these direct to the position that we want. Now, one might be tempted to think about this and go back to a directing group that could perhaps accomplish this. You could write this retrosynthetically, because if you have the aldehyde, it's a meta director, and you can put the bromo on meta. And we know how to reduce a CO to CH2 with palladium on carbon, for instance. So would this work? Well, let's think about it for a second. If we consider the forward reaction, which would be to start with benzaldehyde, and the initial reaction, so you could imagine if we're going to do this, we might write 2 Br2s, FeBr3, and we can use the meta-directing aldehyde group of benzaldehyde to achieve this. But let's look at it a little more carefully. So would this give me this compound? Well, of course, the first thing we have to do is monobrominate. So let's look at the monobromo compound. Just going to rotate to make it easier to write. If the bromine goes on meta, that's one, and they go on one at a time. Now we have our conflict resolution problem to solve. Do you remember that for multi-step synthesis to make tri-substituted benzenes? Again, it's tempting to look at this and go, well, I can put 2 bromines on. But once I get the first bromine on, I have a new problem. I have 2 different directors. The aldehyde directs meta. Okay, that would be good. The bromo directs ortho and para. But which dominates the chemistry? The least deactivating, which is the halogen. So this is a conflict resolution problem with a meta issue. So we do not get substitution at the position that has 2 ortho substituents. So in fact, the second bromine on this does not go in the desired position to make our target molecule. So the first bromine went here, but the bromine dominates, so I'm either going to get this dibromide and a mixture, if you remember what our rules taught us. There's that first bromide, the second one could also go here. So neither of those will produce a major product that's our desired product. So you see, this doesn't work by classic electrophilic substitution. So now we have to see that substituent that wasn't there, that isn't there. Okay? And we can see this one in terms of retrosynthetic analysis. If we come back to a diazonium in this position. Okay, because we just learned in the other part of section 24.8 how to turn a diazonium into hydrogen, right? What was the reagent we needed? Hypophosphorus acid, right? In the forward direction, we would be writing this H3PO2. Now, if we think back again, The diazonium would have come from because we know how to diazotize. So again, I'll write the forward chemistry here would have been H2SO4 perhaps, and HNO2. Remember, this is nitrous acid, not nitric acid. You should look at the mechanism for diazotization. I'm not going to do it explicitly, but you should be able to work out that mechanism now on the basis of fundamental principles of acids and bases followed by electrophiles and nucleophiles. All right, at this point we know that the amino group, again we learned in this chapter, it's so activating that it puts on both bromines no matter what I try to do. But in this case, that's exactly what we want. Right? And of course we could write that chemistry in the forward direction. All we need is Br2. The amino group is so activating that it puts both bromines in. Of course you can't substitute the methyl. There's no hydrogen there. Of course we know now how to take off that. We would first convert it in what's called a functional group interchange. From the nitro group. And what chemistry could you use here? There are a number of different reagents, but the new one that we've learned recently was 1SnCl2, stannous chloride, tin 2 chloride with HCl, followed by neutralization in the workup with sodium hydroxide will achieve that reduction. Now we're back to a classical electrophilic substitution. We could take the nitro group off, and we know that the methyl group being an ortho-para director, and toluene's far enough back for us to go here. Of course, the conditions for nitration we learned a few chapters ago, HNO3. Right? Notice the 3 there because we need nitric acid for this with H2SO4. All right, so I've kind of thrown in the synthesis. You should sit down, look at some problems like this. There's a really good worked example in our textbook, and recognizing that the key, right? The key to using the diazonium, okay, is when the directing group effects are wrong. Okay? And I put wrong in quotes, right? Because in electrophilic aromatic substitution, bromine does not direct meta, methyl does not direct meta, and that's what I mean by the wrong directing group effects. Then you can learn to see there was a substituent that's not there now that I needed before, and you can turn one of those hydrogens into a nitrogen. The other thing is recognize the symmetry. Okay, the symmetry actually tells you where typically the symmetry will tell you where that substituent needed to be. All right, that's multi-step synthesis.